Hello everyone, welcome to section 3.4 where we're going to finalize chapter 3 material. So the first thing we're going to introduce in this chapter are factorials. Now factorials are just a count of the number of ways that we can order n objects without repetition. Now this is basically what we did when we had that book problem. We were putting 5 books on a bookshelf and we had 5 selections for the first book, 4 selections for the second book, so on and so forth. So this is defined. And first of all, you say that you're doing a factorial by doing exclamation point. So n exclamation point would be whatever value n is, factorial. And this is defined as n times n minus 1 times n minus 2 times, and then so on down to 3, 2, 1. So basically what this means is just that we are going to take whatever value we have for n, our factorial, and we're going to multiply it by every descending number until we get to 1. So an example of this might be if we had 5 factorial. So if we were to write out 5 factorial, it would be 5 times 4 times 3 times 2 times 1, which is equal to 120. Now, let's actually look at what would it be if we had 6 factorial. This would be 6 times 5 times 4 times 3 times 2 times 1. And the reason I wanted to show you this is actually one of the really useful principles of factorials, is that if you look at this part of 6 factorial, it's just the same exact thing as 5 factorial. So instead of writing 6 factorial as 6 times 5 times 4 times 3 times 2 times 1, we could instead say that it is 6 times 5 factorial. Or we could take it one step further and say that it's 6 times 5 times 4 factorial. Or it's 6 times 5 times 4 times 3 factorial. And you might wonder, why do we want to do this? Well, one, for example, in this first case, if we already know what the number is, it makes it easier. What's 6 times 120 instead of doing 6 times 5 times 4 times 3 times 2 times 1? Another reason is whenever we're doing combinations in the same section, I'll show you how this can actually make it very easy to calculate by hand, even if you didn't have a calculator. Now, a couple other things I want to mention about factorials before we begin doing some problems is that if you have 1 factorial, this would just be equal to 1, right? Because it's 1 times every descending number down to 1, it ends up being 1. Similarly, 0 factorial is also equal to 1. And you can think of this as a number of ways that you can arrange in objects. So what this is saying that 5 factorial means that if I have 5 objects, how many ways can I rearrange them or arrange them where every single object is used? And there's 120 ways. If I have 1 object, how many ways can I arrange it? Well, there's only 1. I just put the 1 object. I place that. If I have 0 objects, how many ways can I arrange it? I have 1 way. I have no way to arrange it. So in the end, 0 factorial is 1 for when you're doing factorials. So second example we have on this slide is, how many ways can someone arrange 4 books on a shelf? So last time we did is we wrote out the different shelves and we said, okay, I have 4 books and I put it in, then I have 3 books to choose from and I pick one. But this time we're just going to say that it's 4 factorial, which is equal to 4 times 3 times 2 times 1, which is equal to 4 times 3 is 12, 12 times 2 is 24. Okay. Next question asks you to express n factorial in terms of n minus 1 factorial. So this would just be that n factorial is equal to n times n minus 1 factorial, right? This is just using this principle that we covered here, that I can actually write this in terms of any of these. So I could do n times n minus 1 times n minus 2 factorial. By the way, don't let the n minus 1, n minus 2 throw you off. All it's saying is whatever value n is, let's say it's 5, the next value is that minus 1. So 5 minus 1 would be 4, n minus 2, so 5 minus 2 would be 3. It's just telling you that it's the next number lower. Okay, what about if we had 5 factorial divided by 4 factorial? So we could write this out as 5 times 4 times 3 times 2 times 1 divided by 4 times 3 times 2 times 1, and then we could get cancellation for a bunch of terms. Or we could have just instead done 5 times 4 factorial divided by 4 factorial. And this would leave us with 5. For 7 factorial divided by 4 factorial, this would be equal to 7 times 6 times 5 times 4 factorial divided by 4 factorial, which would just be 7 times 6 times 5, which is 210. And this is, again, why this can be very useful. Now, one thing I will warn you about is that factorials can get out of hand very quickly. For example, right now, if you have a calculator with you, I would suggest try typing in 100 factorial and see what happens. You're probably going to get some sort of error, an overflow error, syntax error, something like that. And this is because they grow very, very, very quickly. In fact, a long time ago, even computers wouldn't be able to do 100 factorial. So that's one thing to always keep in mind with factorials. Now that we've covered factorials, we're going to look at permutations. So a permutation is just one of different arrangements of a group of items where order matters. And that's the key part about permutations. Order matters. Basically what you're doing is you are looking at, if I have some number n objects to choose from, how many ways can I arrange some subset R of those where order matters? And the way that we would write this is it's going to be n capital P R for n permute R. So basically all this means would be something like, let's say that I had 10 people to choose from, and I need to pick 3 of them to make a committee to represent the class. The first person that's selected will be the president, second person selected will be the vice president, third person will be the treasurer or secretary, something like that. So in this case, let's say the people were A, B, C, D, E, so on and so forth. A, B, C would be a different group than A, C, B, or B, A, C. These would all be different groups because in this first one, A would be the president, B would be the vice president, C would be the treasurer. In the second group, A would be the president, C would be the vice president, B would be the treasurer. So even though these are made up of the same people, they are considered different. So a permutation is one where you're taking some R number of objects from a total of n objects and seeing how many ways you can arrange them where order matters. So the way we actually find a permutation is just going to be n factorial divided by n minus r factorial. So let's look at an example to kind of illustrate how we would use this. Find the number of ways that we can arrange 4 people in groups of 3 at a time where order matters. So we have a total of 4 people, and we want to select 3 of them where order matters. So in this case, 4 is my n. So I'm going to plug this in. 4 factorial divided by, n is still 4, minus, well, my r is 3, so 4 minus 3 factorial. This would give me 4 factorial divided by 4 minus 3, which is 1 factorial. So 4 factorial is just going to be 4 times 3 times 2 times 1. 1 factorial is just going to be 1. So this is going to be 4 times 3 is 12 times 2 is 24. And if you look at the slide, you can see an example of all these different groups we could get. ABC, ACB, BAC, BCA, CAB, CBA. Those are all the groups that have A, B, and C. Then you've got the groups with A, B, and D. You've got the groups with A, C, and D. And you've got the groups of B, C, and D. What I really want to focus on, though, is I want to really focus on combinations, because we're actually going to be using this a lot more. Combinations start with the same basic idea as a permutation, where we have some n number of objects or people that we can choose, and we want to select R of them and find the number of ways we can arrange it. But the difference is combination is where order does not matter. What it means then is that, going back to our committee example, it would be I'm selecting 3 people, but there's no position hierarchy. It's just your committee member and that's it. So A, B, and C would be the same exact committee as A, C, B, which would be the same committee as C, A, B. It doesn't matter what order they got picked in, they are the same group. There's no difference between them. So the way you find a combination is, first of all, we write it as NCR, or more likely, how you're going to see when we do chapter 4 that I'm going to write it, is we're going to do it this way. N choose R, where it's N over R in parentheses. This just means do a combination. So we do binomial distribution. This is how I'm going to be writing it. This is how I generally write combinations. Now, one thing I want to point out real quick, a little side, is if you were looking at using certain advanced calculators or you're doing this on a computer, you may see permutations sometimes as P, comma, parentheses in R, and you may see combination as C in comma R. And this is just because when you're typing in like a computer or something, you might not have a special way to put this, but you could type this. You could put C parentheses, type your value, comma, value in parentheses, and it'll tell it to do a combination. Okay, so now let's look at the number of ways that we can select 5 distinct cards from a set of 12. Now, the way you actually solve for a combination is going to be n factorial divided by n minus r factorial r factorial. Now, if you look at this part right here, this n factorial divided by n minus r factorial, this should look familiar to you. This is the same thing as saying we are taking the permutation and dividing it by r factorial. And it is just that. A permutation taking some subset r from a total sample set of n things where order matters, we take all those and we just divide out all the repeats. So going to our prior slide, you will see that when we grouped them, we had the ABC group, where ABC, ACB, BAC, BCA, CAB, and CBA. The combination sees all of those as one thing. They are all the same group. So order does not matter. So then going to that example on the slide, instead of having 24 different ways that we could pick 3 people from the 4 where order matters, we now only have 4 ways that we can choose them if order doesn't matter, which is we could have the people A, B, and C, we could have A, B, and D, we could have A, C, and D, and we could have B, C, D. Those are the four different possible, let's call them committees, where order does not matter. So in this example, we want to find the number of ways to select 5 distinct cards. So this is going to be our R. R is equal to 5. And we have a total of n equals 12 cards. So we want to find, I'm going to write the first one this way, and then we'll do the second one using my other method. We want to find 12, choose 5. So if we write this out, this will be 12 factorial divided by 12 minus 5 factorial, 5 factorial. And now I'm going to show you how you could actually solve this by hand, even if you didn't have a calculator. And this is where the rules of factorials actually come in very handy. So first things first, I'm going to write down the bottom. So I have 12 minus 5 is going to give me 7 factorial times 5 factorial. And then I'll leave this 12 factorial for now. Okay, so now what I would do is I am going to write out and expand the top, the numerator, up to the largest factorial. So this is going to be 12 times 11 times 10 times 9 times 8 times 7 factorial. On the bottom, I'm going to leave my 7 factorial alone, my biggest factorial, and then I will write out the smaller factorial. 5 times 4 times 3 times 2, and then times 1, even though it doesn't have any impact. Now you might wonder, why did I do this? Well, by taking this down to the bigger factorial that's in the denominator and leaving the bigger factorial in the denominator, we can now cancel those out. So 7 factorial is taken off from the top and the bottom. And now what I'm going to do is I'm actually going to do some cancellation of my bottom terms that I expanded out with the top terms that I have. So an example of this might be, I could take 5 and 2 and cancel 10. I could take 4 and 3 and cancel 12, and I'm left with 11 times 9 times 8, which is a lot easier to figure out than all of this, right? For example, if I took 8 times 9, that gives me 72, And then I just had to figure out what 72 times 11 is. So 72 times 10 would be 720, plus 72 would be 792. And you can see that I did that without having to pull out a calculator. And even though I have the slides in front of me, I didn't even use the slides to find that number, because this is why this can be very useful. And that's why I kind of mentioned it when we were doing factorials, of why that specific aspect of it can be very helpful, because it simplifies problems like this. Okay, the final example on this is to find the number of ways you can select a 3-member committee given a group of 4 people. And we actually did a problem like this. So if you went back to the prior slide, you will see that we had 4 possible committees made up of 3 people where order does not matter. Now, we already talked about this, that a combination is just a permutation where we divide out all of the repeats by dividing by r factorial. When you're determining whether you are looking at a combination or a permutation, oftentimes it's going to be based on the language. If you see the word arrangement, that oftentimes means that you are doing a permutation. If you are seeing the word selection, that means that you are looking for a combination. Before we move on to examples, I actually wanted to kind of show you a pattern that emerges when you're doing combinations. So let's say that we had a total of 6 objects that we could choose from. If we do 6 choose 0, we're going to get 6 factorial divided by 6 minus 0 factorial times 0 factorial. Now, 6 minus 0 is going to be 6. So we're going to get 6 factorial over 6 factorial. 0 factorial is going to be equal to 1. So this means that it is going to be 6 factorial over 6 factorial, which means that we have 1. And what this really kind of translates to is, if I have 6 objects, how many ways can I choose none of them? Well, I have one way I can do it. I don't choose any of them. But if I choose 6, let's do this one. We would get 6 factorial divided by 6 minus 6 factorial times 6 factorial. So like before, 6 minus 6 is going to give me 0 factorial. So this term is going to go to 1. And we're going to get 6 factorial over 6 factorial, or 1. And this is the same idea as what we did when we chose 0 objects. If I have 6 objects, how many ways can I choose all of them when order doesn't matter? Well, I have one way I can do it. I can choose all of them. If we do 6 choose 1, we're going to get 6 factorial divided by 6 minus 1 factorial, 1 factorial. So we're going to start with that 6 minus 1 factorial. That's going to give us 5 factorial. 1 factorial is just the same thing as saying 1. And then I'm going to do what we talked about previously. I'm going to take 6, and then I'm going to go down to my biggest factorial, which is that 5 factorial. The 5 factorials will cancel, and I am left with 6. So what does this mean? Well, it means that if I have 6 objects, how many ways can I choose one of them? Well, I have 6 ways I can do it. I can choose the first one, or I can choose the second, or the third, or the fourth, or the fifth, or the sixth. If I have 6 choose 5 objects, this is going to be equal to 6 factorial divided by 6 minus 5 factorial, 5 factorial. Well, 6 minus 5 factorial is going to be 1 factorial, so this is going to go to 1. So I'm going to get 6 times 5 factorial divided by 5 factorial, which is equal to 6. What this translates to, if you were thinking about it, would be if I have 6 objects, how many ways can I select 5 of those objects where order doesn't matter? Well, you could kind of reframe this question as, if I'm selecting 5 of the 6 objects, then how many ways could I not select one of them, right? I could not select the first object, or I could not select the second, or the third, or the fifth, or fourth, fifth, or sixth. So you'll notice they're actually kind of the same problem. And this pattern holds true. If I do 6 choose 2, this will be 6 factorial over 6 minus 2 factorial, 2 factorial. this is going to be 6 times 5 times 4 factorial divided by 4 factorial times 2, because 2 factorial is just 2 times 1. The 1 doesn't have any effect. The 4 factorials cancel. This is going to be 3 times 5, which is 15. If I do 6 choose 4, this is going to be 6 factorial over 6 minus 4 factorial, 4 factorial. 6 minus 2 factorial is the same thing as saying 2 factorial. So this is going to be 6 times 5 times 4 factorial divided by 2 times 4 factorial. The 4 factorials cancel out with this, and we get 15. Now you may be seeing a pattern, right? As we were at our outer values, choosing 0 or everything, we have an outcome of 1. If we're choosing 1 or everything minus 1, we get an outcome of 6. If we choose 3 or everything except for 2 of the objects, we get 15. And it's going to follow this pattern. When you're doing a combination, it will always look something like this. If we were to draw a histogram to kind of represent it, is that they will always be equal as you go out from the center term. Or I like to do these ones from the outside. And this is because n choose anything, so n choose 0 will always be 1. N choose n will also always be 1. N choose 1 will always be n. N choose n minus 1 will always be n. And then from there, it just follows that every one that you go in will be the same value. The only exception to this might be that if you have a single center value, like if you have an odd number, this one will be different. If you have an even number, then it will be the same because it's going to be the same as the other middle number as you move inward. So you can kind of think of it as there's one way I can select 0 or n, there's n ways that I can select 1 or n minus 1 objects, and so on and so forth. So the last thing I want to do for this is I do want to show you that this does in fact work for any n. So if I do, actually let me erase this real quick and then I'll do that for you. Okay, I'm going to show this to you in terms of n to show you that this is true no matter what size you're picking from. So n choose 0 will be n factorial divided by n minus 0 factorial, 0 factorial. So again, 0 factorial will always be 1. N minus 0 is still n. This will give me n factorial over n factorial, which is equal to 1. If I did n choose n, this would be n factorial over n minus n factorial, n factorial. N minus n will give me 0. 0 factorial gives me 1. We're left with n factorial over n factorial equals 1. If I did n choose 1, this would be the same thing as n factorial over n minus 1 factorial, 1 factorial. Again, 1 factorial is just 1. I'm going to put my n factorial in terms of n minus 1 factorial. So this would be n times n minus 1 factorial over n minus 1 factorial leaves me with n. And the last one I'll do, and then you can kind of see that it extends from there. If I have n choose n minus 1, and this is going to be equal to n factorial over n minus, so now I have to do n minus 1. Well, if I am taking the negative of this, it's going to be minus n plus 1, right? Because if I had n minus 1 and I do negative, if I distribute that negative, it's the same thing as saying minus n plus 1. And then this is factorial, and then n minus 1 factorial. So solving for this, n minus n, this goes to 0, and I'm left with 1 factorial, which is equal to 1. So this gives me n factorial divided by n minus 1 factorial, which, as we did last time, would be n times n minus 1 factorial divided by n minus 1 factorial equals n. So this is true for no matter what size sample you have. If you have 100, 100 choose 0 will be equal to 1. 100 choose 100 will be equal to 1. 100 choose 1 will be equal to 100. 100 choose 99 will be equal to 100. And then for every step you come in, they will be the same outcome. They will be the same value. Okay, let's look at 2 examples and then we'll be done with this section. Suppose we have a group of 10 people consisting of 6 women and 4 men. How many different combinations of people can we choose for some committee? So we want how many 4-person committees can we choose? So this would be, there's 10 total people, choose 4. So this would be 10 factorial divided by 10 minus 4 factorial, 4 factorial. So 10 minus 4 is going to give me 6. So like I said, I'm going to go down to the larger factorial, which is going to be that 6 factorial. So 10 times 9 times 8 times 7 times 6 factorial. 10 minus 4 is 6, so 6 factorial. And then I'm going to expand out this 4 factorial. 4 times 3 times 2 times 1. The 6 factorials will cancel. And then I'm going to do some cancellation with the other stuff. So 2 and 4 will cancel out the 8. 3 will cancel out part of the 9, and I'm left with 10 times 3 times 7. So 3 times 7 is 21. 21 times 10 is 210. Second part of the question asks you for how many 4-person committees are there consisting of 3 women and 1 man. So in this case, of these 4-person committees, how many of them, so what number of committees could we get that are 3 women and 1 man? Now, if you remember from our prior section, when you see that intersection or and, that's the same thing as saying we need to multiply. So we're asking is, if I have a committee, how many ways can I pick those 3 women from the 6 women that I have, and how many ways can I pick 1 man from the 4 that I have? And then we're going to multiply those to get how many committees I can make of both. So first things first, let's see how many possible ways we can select these 3 women. So we have 6 women to choose from, and we're selecting 3 in the committee. And we have 4 men to choose from, and we're selecting 1. So this means that this first one, the women, are going to be 6 factorial divided by 6 minus 3 factorial, 3 factorial, times, in this case, we have 4 factorial, 4 men, 4 minus 1 factorial, 1 factorial. Now, you actually shouldn't even need to do this calculation, though, because we just talked about this. N choose 1 will always be equal to n. So the answer to this part is 4, even without doing the calculation. So really, all I have to figure out is how many ways can I choose 3 women from a total of 6 women. So this is going to be 6 minus 3 factorial, so it's going to be 3 factorial. This will be 6 times 4 times 6 times 5 times 4 times 3 factorial divided by 3 factorial times 3 times 2 times 1. The 3 factorials will cancel. And then I'm going to cancel 3 and 2, cancel the 6, leaves me 5 times 4. So this is going to be 20 ways that I can choose 3 women from the total 6, and then times the 4 ways that I can choose 1 man from the group of 4 gives me a total of 80 ways that I could make this committee of 3 women and 1 man from a group of 6 women and 4 men. So then what is the probability, though, that I would select this committee? So what's the probability that I would get a committee of 3 women and 1 man? Well, going back to our definition of probability, this is just going to be the number of ways that I can get 3 women and 1 man divided by the number of ways that I could get a 4-person committee. I'm just going to call it 4com for 4-person committee. Now, we've already actually found this. Well, we found that there are 80 ways that we could get a committee of 3 women and 1 man from this 6 women and 4 men that we have to choose from. And there are a total of 210 ways that we could form a 4-person committee from the total 10 people meaning that we would have a probability of 0.381. For our last example, we're given that we have 5 women and 3 men. And the question asks, what is the probability that a 3-member committee can be formed with only men? So we want the probability of getting a committee with 3 men and 0 women. So let's set this up. Well, first of all, let's focus on the intersection. That means that it's an and statement, meaning that both must be true at the same time. So we need a committee of 3 men, we need a committee of 0 women, and then we multiply them, right? Because and uses the multiplication rule. So this means that what we're going to be looking for is we're going to be looking for the number of ways that we can get 3 men and 0 women divided by the number of ways that we can get any 3-person committee. So let's break this down a little bit. First things first, let's figure out how many ways we can get that 3-person committee. In our group of total people, right, we have an n of 5 plus 3 equals 8. We want to say how many ways from these 8 people can I choose a 3-person committee. So this is going to be 8 factorial divided by 8 minus 3 factorial, 3 factorial. So 8 minus 3 is going to be 5 factorial. So I'm going to do the top as 8 times 7 times 6 times 5 factorial, and then 3 factorials, 3 times 2 times 1. Cancel the 5 factorials. 3 times 2 cancels with 6, leaves me 8 times 7, which is 56 possible ways that I could make a 3-person committee from these 8 people. Now let's figure out how many ways can I get 3 men and 0 women. So the men first. I have a total of 3 men, and I want to choose 3 men. Times, I have a total of 5 women, and I want to choose 0 of them. Now, we don't even have to set up any calculations for this because we already talked about how we can do this. N choose n will always be equal to 1. N choose 0, right? If I have 3, how many ways can I choose all 3 of them? 1 way, I choose all of them. If I have 5 women to choose from, how many ways can I choose none of them? 1 way, I choose none of them. Meaning that the number of ways that I could get a committee from these 8 people of 3 men and 0 women is only 1 possible way. I choose all 3 men and I didn't choose a single woman for the committee. So now let's figure out what that probability is. This is going to be equal to 1 over 56, which is about equal to 0.018. So is it possible? Yes. Is it likely? No, because you would only expect a committee like this to naturally occur about 1.8% of the time, meaning it is highly unlikely that a committee from choosing between 5 women and 3 men would end up being all 3 men with none of the women naturally, right? It would be about a 1.8% chance of that occurring. So that's it for chapter 3. We've looked at our principles of counting, like our multiplication rule of counting. We have looked at things like the complement and mutually exclusive, independent events, the multiplication rule of probability, the addition rule of probability, and then we've also covered a couple other topics, things like factorials, permutations, and combinations. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.